SwayamPrabha. Digital India. Educated India.
Welcome to the NPTEL online certification course on structural systems in architecture. So, today we are in the module 4 and the lecture is lecture number 18, and today we are going to discuss the intermediate beams and frames, and this is the third lecture of this particular module. Beforehand we have already discussed the intermediate beams and also the deflection of beams. So, the few concepts will be covered in this particular lecture. We will start analyze the fixed beam and we will try to find out the BMD and the deflected shape of the continuous and the fixed beam, and then we will brief discussion will be going to we will discuss brief on the portal frame. So, the objective of today's learning of that we will analyze the portal frame, we will going to evaluate the bending moment diagram of the continuous beam, we will assess the deflection shape of the continuous beam from the BMD, and also we will introduce the portal frame in that order. So, first we will take up a fixed beam. From where we will start the discussion of the deflected shape and the BMD from a continuous or a fixed beam. Actually, all those are come under the category of the indeterminate beam. So, as you know, if I have taken a fixed beam which is having both end A and B are fixed. So, they are restrained, they are not going to move very easily. So, it will going to have all the reactions will be the unknown over here, and it will actually take lot of moment, that is called the fixed end moment, and also the reactions, both the horizontal reactions and the vertical reactions. So, here if you see, in this case we have three equations available for our equilibrium, but we can take all two, because we are not going to take the sigma f x equal to 0, as you know it is all are the gravity or the downward type of a load. So, the unknown reactions are 2 plus 2 4. These two unknowns in the A end is R A and the M A. The moment at A is unknown because it is fixed. Please remember, this is not a hinge, and the reaction is of course unknown. Similarly, the B end is also going to have the similar sort of unknowns, the moment at B and the reaction at B. So, the unknown are 2 plus 2, that is going to be your 4, and your the static equilibrium equations available is 2. So, instead of 3 I am taking 2, because I am not going to take the horizontal reactions, and the degree of indeterminacy of the beam is going to be 2, because it is 4 minus 2. So, 2 compatibility equations is required. Compatibility equations comes from the geometrical conditions and the deflected conditions of the beam, which are known to us. So, we have discussed that one in details in the last lecture. So, here we have to go with the force method, and we will actually going to have two unknowns or forces, two forces will be the unknown. So, to solve this third and fourth unknown, so we will take the R B and the M B, though these two, the R B and this M B, we will assume these two as the unknown value of my the equations, and then I will try to solve by the compatibility equations this R B and the M B. So, to do that, we have to actually create some beams which will come definitely from this mother beam, that is the two end fixed beam, and by superimposing all those the beams that we will create should give me the primarily that the original beam itself. So, what we do here, if you see in the first figure, the no reactions in at B has taken. So, actually this particular the fixed end is removed. So, instead of that, if you remove, there are two things that we are removing, that is RB we are removing and the MB we are removing. So, first with UDL we put that particular beam. So, as the UDL will be there in the beam. So, this beam AB is now changed to a the cantilever beam, and that is a statically indeterminate beam. So, because we have removed the RA and the MB, because we have removed the fixed end itself. So, the delta B1 I have written over here, you see this is the deflection of end B because of the imposed load omega, that is due to the on the length of the beam. In the next, what we have done is that we have no UDL and the no MB has taken into account, only the reaction R has been taken into account. So, I have removed the UDL and also I have removed the MB, that is the moment at B, and I just put the RB. So, I just a support I have put imaginary, and because of that there is a reaction at the top, and as the reaction is at the top RB, there will be a deflection upward which I have marked as delta B2. And finally, I again remove the UDL, and again here I remove the RB, that is the reaction at B. I have placed the MB, that is the last one I have to place. So, a moment has been placed at the end, and due to that again there will be upward deflection, and that deflection I have mentioned as delta B3. And if you just superimpose all these three, you can get the finally the primary beam is this one, because I have removed this RB and MB, then only I got the first cantilever beam, and gradually I have put one after another, and that gives me the totality, right. Now, somehow if I know the values of this delta B1, delta B2 and delta B3, and I know at the end B there is no deflection. So, I have that compatibility. The compatibility equations is that this is the compatibility equation, the deflection at B in the original beam is equal to 0. That means that delta B1, which was downward because of the UDL, must be equal to delta B2 plus delta B3, otherwise there how that particular end B does not have any deflection. So, if you go to the first lecture, this all are derived, this for UDL the cantilever beam, how much is the freehand deflection, that is omega L to the power 4 by 8 EI downward. A pointed load at the free end, what is the deflection, that is RB L cube by 3 EI, that is upward, and if there is a moment at the end at the free end, then what is how much is the deflection, that is delta B3 ML square by 2 EI is a delta B3. So, those we have already discussed in the first lecture of this 4th week. You can go and visit that one also, the PPT or maybe the lecture. So, those are known to us, and now we can just put in all those that delta B2 is this, delta B3 is this, is equal to delta B1 is this, and finally, I will get a equation number 1 which in that equation I have two unknowns. The RB is unknown to me and MB is unknown to me. L and omega, that is the intensity of the load and the span, is known to me, because that will be definitely given for the solving this particular problem. So, this one equation will not going to help me when there are two unknowns. I have to again search for another equation, and that is required because there are two unknowns, two compatibility is required. The next what I will do, that I again find out the same way and try to find out the slope at the end B, because of the fixity at this particular end is MB, the support B is fixed. The fixed support does not have any kind of a slope, it is straight, no slope will be encountered at the fixed end. So, again because of the UDL at the free end, I have found out the slope as delta B1 theta B1, and for a pointed load upward. So, that is for that the delta theta B2 is the slope, that is the other way the slope is delta theta B2, that is also we have found, and also due to the moment here there is a small mistake, this has to be theta b3, theta b3 is typing mistake is there, theta b3. So, ml by ei, that is also there. So, if you see these slopes are counter, this is this way. So, these two are opposite direction, slopes are in opposite direction. So, similarly, as the theta, as this particular end b is equal to 0, slope at b equal to 0 because of the fixity, that is my second compatibility equation. This is the second compatibility equation. Similarly, I put the values, this is the theta b3, this is the theta that is the theta b2, this is theta b3, and this is theta b1 because of the UDL. So, I put everything. This is also we have discussed in the first lecture, deflection and slope in the of the beams. You can go through that lecture and find out. And finally, I got the second equation ready. So, those two equations, equations number 1 from the deflection 0, equation number 2 from the slope 0 can be solved, and this solutions is just two numerical linear equation solving. It is nothing new to you, and first I have found out the RB, which is WL square by 2, and again the MB, which is omega L square by or WL square by 12. So, this particular MB is hogging, negative moment will be occur over there, and this moment are in the MB and MA will be same, and RA and RB will be same because of the symmetry. So, this WL square by 2 or omega L square by 2, whatever you called, those are negative. So, it is the hogging moment. So, that will create a tension in the top, right, and this is called the fixed end moment. Why fixed end moment? Because both ends are fixed in this particular beam, and this because of that the fixed end will actually encounter this much amount of hogging moment because of a UDL over a span of L. So, now I put all the values which I have just now got, the RBs and the MA and MB, which both will be equal. So, I have written over here, due to symmetry these two has to be equal. Now, let us first let us one after another find out the bending moments and all. So, what I did is over here I take a section X from end A and I try to find out how much is the bending moment at this particular dotted line, right. So, this mx, that x at this particular section, the bending moment x, mx is equal to WL by 2x. This WL by 2 is a reaction. So, this is into x, this is into x minus WL square by 12. So, that is going to be your that is there is a small mistake. I think this is not a small mistake, this has to be 12, not 8. So, those are everything has to be in the PPT. I will make all the corrections. So, this is has to be 12, this all has to be 12. This is not a small mistake, this is a very big mistake. I understand, but I will rectify this in PPT. So, this is here in the equation it is correct, WL square by 12 negative and WX square by 2, that is the due to the UDL, W into X is the total load and that is at a distance x by 2, that already you know. So, this is the expression of your the bending moment expression, and at the midspan I am interested to find out what happened the bending moment at x equal to L by 2. So, I put x equal to L by 2 in this equation and finally found out that this midspan moment is positive and that is a sagging kind of a moment. So, at the end it is hogging, that is the tension top, but finally when it comes into the center it is actually the hogging. So, as and when this is from hogging to sagging is created, so definitely there are some 2 points over there where there will be no bending moment points or the point of counterflexion, a point of inflation. So, that we need to find out. So, finding out the 0 bending moment, so again this has to be your 12 and this is to be 12, everything I will correct and send it in the PPT definitely. So, this particular bending moment equation I put that equal to 0 to find out exactly the location of the x equal to x, that where this bending moment is equal to 0. So, by equation solver or solving the equation, this is a quadratic equation of x. So, you require the solution through the Sridhar Acharya's rule, and finally, the x equal to 211 L is the length of the x from the each end where this particular things will be 0, the bending moment will be 0. So, it will be look like this. So, this bending moment is minus negative, and this is the positive W L square by 12 24 will be the positive, and these are the point where the point of contact flexure or the change over is going to happen. So, those are the hogging moment area, and that is the end of those from that point to the end is the hogging moment area, and central point 6 times L, that is the 60% of the central span will be under the sagging moment, tension bottom, and the 20% in the ends, total 40% of the total area or total the span of the beam will be under the hogging moment tension top. So, now let us see, I have again drawn that one in a other way. So, this is curvature is hogging in the curvature where the tension top and the radius of curvature is downward, and in case of the sagging the curvature is such a way that the tension is in the bottom. So, the radius of curvature is on the upward side. So, that also I have drawn over here to show that there is a change over counter flexure, or there is a change over the of the bending moment sign. So, now that means if I again go back, that means in the hogging area the tension will be in the top. So, if it is a concrete beam, you know that concrete is very weak in tension. So, that will going to there will be crack will appear, right. And whereas the hogging area, so in the area where there are this hogging moments is encountering to the beam. So, there will be some cracks will be developed in the top. Whereas, in the 60% of the area, 60% of the length span where there is a sagging moment, where there is a bending moment in the bottom. So, there is not bending moment, sorry, the tension is in the bottom. So, if it is a concrete beam, so there will be we are expecting some tensile crack in the bottom fiber. So, the crack I have drawn over here, you see this is in the bottom because of the tension, this is the tension zone, this is the tension zone. So, the crack will going to appear. So, the reinforcement has to be placed over there, and we have to design for that. We have to calculate how much reinforcement is required. So, we have to stitch those crack by the perpendicular to that crack. We have to put the reinforcement that such a way that reinforcement is also going to take the tension for tensile stress. So, that is why it is important to find out the amount of bending moment, and amount of bending moment is not always due where actually it will be occurring, hogging or sagging. Then from that point of view we can give the reinforcement properly, right. So, I have another two bending the fixed end moment equation ready for you. You can you can go through lot of books are there, and those books given will give the lot of such formulas for fixed end moment. So, if there is a UDL of length A, other length B is empty. So, what is the amount of M A and M B? If there is a load, eccentric load at A and B, then what is the amount of M A and M B? So, those are there. So, we have some homework today with this particular two the formulas also. So, you can use that in the today's homework. So, in case of the BMD, if I want to draw a BMD, so suppose this is a uniform, I mean it is a continuous beam, and the both ends, the last two A and B ends are of simply supported. So, because of that, and there are suppose some loading also I have given some kind of a span also 5, 3 and 4 meter. The first span is under UDL 16, the last third span is under UDL of 30, and the central span is under a central pointed load of 60, right. And because of this particular the character of the beam, I can at least say that at the end B A and end B, that is the two extreme end of this continuous beam, the moment is equal to 0, because these two are the hinge support. But even though the C and D are the hinge support, central hinge support, because of the continuity of that particular beam, because it is not going to stop at C or stop at D. So, it is continuous. So, there will be a kind of the hogging moment will be created, and that moment we have to find out, and that moment we have found out in the last lecture in the continuous beam. Of course, there was two span and central span we have found out. So, in this particular case, suppose there are two type of moment you have to encounter. One called the support moment, which is your this MA, MB or those here it will be MC and MD, something like that. Here it is MA and MB will be 0, that we have just now discussed. Support moments are, suppose this assume, I have written that assume value, you have to solve that the earlier beam with this particular two unknowns and all. So, I am not going to solve it. Suppose that assume value is 20 and 40 and those are hogging, definitely hogging, because those are the support moment and that will be definitely a, because of the continuity it will create a hogging kind of a moment, that is the tension will be in the top, right. And suppose at C it is 20 and at D it is 40. So, I can just draw this polygon kind of a thing by joining 0, 20, 20 to 40 and 40 to 0. Now, in the next case I can see the span moment. Span moment means I will take this AC as a I mean I do not see that, I will take this AC as a simply supported case. Again I will take CD as a simply supported case. Again I will say take a DB as a again simply supported case. Even if it is this end A is fixed, still I will take the AC as a simply supported and CD as a simply supported, like that. Even the B is fixed, then I will take the DB as a simply supported case. Okay. Another point I must tell you, the end A and end B may be a fixed, but end C and end D cannot be a fixed, because the central support has to be a simply support or has to be a continuity support, and this two has to be a fixed can be fixed support A and B. So, those if I take the AC or CD or DB as a simply supported case and I can find out the simply supported bending moment, that is called the span moment and which is sagging. So, what will be the simply supported span moment for the AC? AC will be WL square by 8 because of the UDL, and that is 50. What will be the span moment for the CD? It is a triangular case and it is PL by 4. So, it is 45. And what will be for the DB? It will be again WL square by 8, but the values changes, L is 4 meter and W is 30. So, that will be 30. So, those are I have drawn in green because it is positive, and earlier was 40 and 20 was drawn in red because it is negative moment. Now, I have to superimpose these two. I have to superimpose these two. So, I have superimposed the support moment and the span moment. Now, see, so because of if you just draw it into the scale, so there will be some ups and down and there will be some hills which will be popping up and there will be some valleys also, something like that. So, here you see this green color which is the above and the rest of the above from this red color, the support moment, those are positive area, the positive bending moment diagram area. The positive means the sagging moment area, that means the tension in the bottom, those area, and rest which is still red. So, it is a superimposed, those small two portions near the support will be till red, and those will be the hogging moment area or the support moment area, or it will be the tension top areas or so. So, here now I am interested to find out how much is the actual moment in this green area. So, I know this is I have to find out the average. So, this 10, 30 and 20, these three are the average of the this red, that is the span support moment. So, how I got? Because this is 0 and this is 20, at the center if it is go straight way or the linearly it will go 10, it will give me 10. So, this is 20 and this is 40. So, at the center it is 30, you can find out like 20 plus 40, 60 by 2, 30, and this is 40 and this is 0. So, at the half it is 20. Now, at here it is 10 and at here it is 50. So, definitely the green zone, green depth is 40, 50 minus 10, right. Here it is 45 and 30. So, that means definitely this is going to be your 15 plus 15, okay. And here it is your 10 because 20 and 30. So, 40, 15 and 10 are the central moment or the span moment form, and from that 40, 15 and 10 you have to design the beam, and in the support moment you have 20 and 40. So, here if I again draw the beam, so this will be the deflected shape. I told this will be the tension top, this is this area is tension bottom. So, this is the span moment, this is tension top, and this is 0 moment case. So, here you see I have dropped down. So, if I drop down, the beam is divided into various sections. So, this in between this zone, this is -20 and -40, that is the hogging case, which is very near to the support and over the support, and the other areas are of +40, that is this portion is +40 as the design moment is +40, because that is the highest moment you have to encounter throughout of this from this point to this point, and this is +15 and this is +10. So, by virtue of that, if I now draw the beam, I just put the support just below C, below D and below A, B. So, then you just project. So, I need the top reinforcement over there. Why top reinforcement over the support? Because I have to encounter -20 over there. -20 means there will be some crack over here, -40 means there will be some crack over here, but here +40 means there will be some crack in the bottom, right. Crack will be in the bottom because of the it is sagging case. So, I have to put the reinforcement accordingly in the bottom. So, like that we have to put the reinforcement. So, that is the finally what we can get it from the analysis, and then we are ready those data, this all +40, the zone, the point where it is actually going to behave like a hogging or sagging, those are the point of counterflexure point. Those are the actually outcome or the output of the structural analysis, and then that will be taken to the next stage of the structural design. So, in some of the cases, in some of the books or some of the handbooks, we can get some kind of a bending moment coefficient. So, for a the continuous beam or for a fixed beam, there are some other coefficients also. So, for a continuous beam which is simply supported in the both the ends, having all spans are equal and having equal amount of loading, which generally comes in a building like the hostel or the similar sort of spans, that is the hostel rooms or maybe the hotels or maybe the suppose some shopping arcade, those kind of regular interval columns or so. In that case, we can go with this kind of the coefficient method also. So, those are available in the books. So, how to use that coefficient I will tell you. So, this coefficient will be written below the support, that means that is the reaction coefficient. Suppose something will be written in the below the beam span. So, that means it is the span moment, that is green, positive, sagging, and there will be something will be written in the above the support. So, that will be the support moment coefficient. So, suppose if I have a the equal span of 4 meter and having a they are carrying a 12 kilonewton per meter UDL. So, this capital W is a total load on the span. The total span load is 12 into 4, 48 kilonewton, right. So, per span it is 48 kilonewton load, because 4 meter is the span and 12 kilonewton per meter is the load intensity. So, for the support reaction, how can I get those reaction has to be multiplied by the 48. See, this 0.339 has to be multiplied by 48. This is my 48. Then here it is 1.214 is multiplied by 48. Like that, if you multiply, so you will get this particular support reactions ready. So, support reactions are required to design it for the shear. And similarly, you can also go to get the span moment. If I just multiply this point, this is for the support moment, sorry. So, if you just 0.161 has to be multiplied with 48, so you will get 7.73 and the next 1.101. So, this will be the second case. So, like that, if you just multiply with this kind of this total moments, you will get. Similarly, you can get the span moments also, that 0.17 now is going to multiply with 48. 0.116 is now multiplied with 48, like that. So, you will get all the span moments. So, now you can superimpose, you can find out the average value, we can find out the central value of this, and then get that coordinate. Just we have discussed, you can find out the design moment. So, finally the portal frame. In the portal frame is a frame. This is a what you have seen here in this particular PPT is the simplest kind of a portal frame, which is having 2 columns and 1 beam. This is also called the moment resisting frame, and this particular frame is analyzed because of the axial force and also shear force and the bending moment. So, all the 3 types of forces it will carry. It is not like beam. Beam does not carry the axial force. Beam carries bending moment and shear force. Truss carry only the axial force, but portal frame carry all the 3. and this portal frame can be analyzed for the gravity load and the lateral load. So, suppose these are the 3 unknown value because it is fixed. So, this will give you 3 unknown values, 2 the upward directions, 2 horizontal directions and 2 moment. So, if it is fixed, so the degree of indeterminacy is 3, 6 minus 3 is equal to 3, because now here I have to take 3 because I cannot ignore the horizontal directions over here, right. So, and in the portal frame sometimes we may say it is the bay and story. Bays are the in horizontal run how many portals are there, and the stories how many the beams are actually cutting down those columns. So, those are the stories. So, in this particular figure we have 1, 2, 2 bays and 1, 2, 3, 4, 4 stories, 1, 2, 3, 4, 4 stories and 2 bays. So, there are different type of portal frames. So, this first one can be indicated that this can be used in kind of factory and those kind of area. The second one is proper, this is a proper kind of a this thing. This can be used for a kind of hilly areas when there can be the differential height of the portals column, and there may be sometimes we may have some discontinuity. So, there may be the headroom, this is headroom available, 2 floor open headroom kind of a thing, those kind of things are also possible. And this particular portal frames are designed for the gravity loading which was downward, and also for the lateral loading which is sideway push because of the earthquake or maybe for the wind. So, bending moment diagram for the portal frame is also we will not going to in detail, we will going to discuss. So, here what is going to happen, this is bent such a way that the bending moment profile is like this, like a these columns will have a sway and the beams will have a that kind of a the simply supported bending moment kind of a case fixed in this case. And in case of the sway that can in the lateral kind of a load, it will have this kind of a bending moment diagram. So, for this probably you have to if you want to understand this, you have to actually go through the proper structural analysis subjects. In some of our professors has this particular subject in the NPTEL, you can refer those. So, that is all for this particular lecture of analysis of continuous beam or analysis of beams and indeterminate beams and frames. At last we must conclude like the bending moment diagrams of a fixed and continuous beams consist of both sagging and hogging, that we have understood, and the nature of bending moment provides the deflected shape of the beam and the reinforcement zone of the beam, and that can be marked accordingly. So, before we finally end, we have 2 homework for you. So, I have just now told you there are 2 formulas I have given in the particular PPT. You have to find out the fixed end moment for both the beams, and also you have to sketch the bending moment diagram for the following beam, and perhaps you can also try to find out the what should be the reinforcement pattern of the particular beam, as it is a case of a fixed beam, both end A and B are the fixed. And in the second case, draw the bending moment diagram for this particular beam. If you have the support moments at A and C are 20 and 30, that is I have given as an assume, it is a assume case. So, sketch that particular bending moment diagram. So, assume that this is going to be your minus 20 at A, and at C it is going to be minus 30, and definitely at B it is 0 because it is end is a simply supported case, and because of this so there will be something like this kind of a not like this. So, erase all. So, it will be 20, it will be 30 and it will be 0. So, something like this will be the bending the negative diagram, and in this case this will be your positive diagram. So, you have to find out those values in this particular case. Thank you very much.